first. So I will share my screen. So is it clear to you, the desktop?
Can see it. Yeah.
You can see, yeah. Let me see where is the project last time. Okay, so I think this is the model we have last time, right? Okay, so today I will continue from here. Okay, then I think the main purpose, is it started recording? Okay. I think the main purpose for today's session is to show you that how do we model a queuing system, a simple queuing systems, okay? So in order to do so, let me just briefly introduce to you what is the simple queuing system we're going to simulate today. Okay, so I need to open one more slice. Okay, so let's take this one as an example. Okay, so look into this model described here. So this one actually called a conceptual model. Okay, conceptual model actually meaning that it's not, I mean, the description of the model is not very precise, but actually it's show you some of the main concept of this system. So basically, when we're looking at the queuing system, it meaning that we actually have a queue, and they are actually queue for some purpose, which are doing some process. So here we can consider a process as a machine, okay? So when a machine process certain, like maybe a product, okay, let's call this as a product. When this machine is used to process this product, okay, then this machine will consume like some time, okay? Because this machine actually has certain capacity, okay? So when there's a certain product comes, then the capacity is not sufficient, meaning that all the capacity is occupied, then those products need to be waiting in the queue, okay? So this is actually the so-called queuing systems. Okay, when the process is finished, then it will actually finish. Okay, then there will be another queue, will be dequeued from here, then join the machine to process. Okay, so this is actually a systems we are going to model today. Okay, but I think before we really like zooming into the model, may I ask a few questions for you to like have a better understanding of the system we are going to model. The first one is maybe just bear in mind that the state, okay, the state of the system is some things you need to think at the beginning, okay, when you look into a system, considering going to model this system, okay. So state is actually is a set of variable for you to decide to define or describe what is happening in the system at a certain time point, okay. Okay, remember this. A state is actually a set of a variable to help you to understand what is happening inside the system. So may I ask this a question? So if you want to look into the state of this system, so what can you see? Okay, what can you see from these systems? Okay, if you imagine that, if you imagine anytime you can stop the clock, you look into this system. So what are the things you can see from the system? Okay, someone can answer me your question. Just feel free to talk about anything.
Stuff in the queue and stuff in the process.
Step in the, sorry?
Queue. In the queue.
Step in the queue or what?
Sorry.
Stuff.
If a stuff, yeah.
Okay. Meaning that all the product or those
okay.
in
product
the
in the queue and product in the
okay.
process.
Okay.
Machine.
So yeah. So in that case, if we just ignore about what are the stuff, okay, so maybe we just say it's maybe we call the load, okay, but actually here they use the load for the is a verb, but usually I mean in our simulation we use a load as a noun to say that these are the items. So maybe we just refer it as loads, okay. So in that case, what are the properties? What are the variables we are looking at? If we only consider that one type of the load in the system, so the property we are looking at is what?
Is it idle and busy?
No, yeah, this is one. This is one. Yeah, maybe this is another one. So just now, I think just now who answered the question is a Hongdan, right? Just
number of the loads.
Yeah, number of the loads. Yes. Number of loads in the queue and number of loads in the machine, right? Yeah, yes. So I think this is correct. This is correct. This is one answer. And also, I think Sijie also answered this correctly. It's whether the machine is busy or the machine is idle. Okay, so this will be another state variable. But also, we can see that there's some relationship between these two. Okay, for example, the number of loads at a process. So if this one is larger than 0, meaning the machine is busy. Okay, so if it's equals to 0, then it's idle. Or maybe it's less than capacity, then it's idle. Meaning a part of it is idle. This is actually defined. So if the capacity is more than 1, so this idle and the busy, we need to give a better definition of it. So a more precise way to define the state variables will be the number of loads, okay, in the machine. But I think both answers will be correct. Okay, any other things? Okay.
Arrival rate.
Arrival, is it something you can see when you stop the system?
Okay.
Yes. I think that would be a very good counter example. I mean, for example, arrival rate is not a state variable. Why? It's because if you are just giving a snapshot of a system, you cannot see the arrival rate. You cannot see the service rate. Okay. Yeah, so I think this is something, but also maybe that in some of the system we can see that, okay, the remaining processing time of the load in the machine is recorded. It may also happen, okay, in some cases, the remaining processing time of the loads in the system is recorded. So in that case, if you take the snapshot of the system, you actually not see the number of loads. You are not only see the the attribute of the loads, but also one important thing is how much time is remaining, okay, for the each of the loads. So this may happen. Okay. So I mean, if you answer this, will also be considered as correct. But in that case, meaning that we need to model more details of this system. Okay. So any other things, okay, regarding the state variable? I hope no. I hope no, because yeah, later you will see that yes, this is actually the main things we want to put into this model lah. Okay, so basically it's the number of the loads in the queue and the number of loads at the machine. Okay, so this will be the main state variable. Okay, so after this, I want to tell you another concept, which actually the concept of the event. So what are the events? Event is actually those things occurring at a time point. Okay, so event itself doesn't have a time duration, does not have a time span. Rather, it occurs only at a time point, which actually is a dimension. Means the timeless, meaning that there's no time dimension on the events. Okay, but what this event do is the event will change the value of the state variable we just defined. Okay, the event is something will change the value of the state variable. So let's look into this way. Okay, to see that just now we have identified the state variable to be number of loads in the queue and number of loads in the machine in the server. So now I want to ask a question: is how many events we will have? Okay, which actually meaning that what is happening that will change the value of those state variables. So can we have some answer on this?
Sir, when the vessel arrives,
Yes. Not necessarily vessel. So here we just say loads. It can be
yes,
vessel, it
yes,
can be anything. Yes.
anything, yes, yes, or
Yes.
customer, anything.
Okay. Yes. Arrive will be one event. So which
The,
state variable it will change?
it will change the buffer because we will then start filling in the buffer.
Okay, we'll start filling into a buffer. So we will change the number of the loads at the queue, right?
Yeah, yeah, we will NQ.
Okay. So okay,
And
so this is a
yeah,
correct answer. Yeah, maybe you'll give opportunity to someone else.
okay,
Yeah,
okay,
so
sir.
who want to be the next to answer the next event? Hongdan, you want to try? Hongdan, try.
No, I'm waiting for answers.
Okay, so who else got the answer? If not, then let me. So yeah, let me check. Who want to answer other events? So
Load.
Joyce, are you there? Yes.
Yeah, load. Then the next is unload.
Yeah, load. Actually, it's a start service, but here, yes, on this PPTs we have load. So which state variable will change?
The number of loads in the buffer and the number of loads in the machine.
Yes, correct. So the load, actually the start service will be another events now we are looking at. Yeah, okay. So yes, so this will be the second event. Any more?
Unload.
Unload. Okay, actually I wanted someone else, but it's okay. So unload. So which state variable will change? Will this event change?
The number of loads inside the machine.
Number of loads inside the machine. Okay. Yeah, that's right. That's right. Okay, so now we actually see that there's a two state variables we're going to model. Then there will be three events. Okay, we are actually observing now. Okay, so this is actually the second concept we need to like answer, or we need to like ask ourselves when we look into a model. So we take that now they take this like a simple queuing system to illustrate the concept. Okay, now the third question is, what are the relationship? Okay, the event will trigger each other. Okay, will trigger each other, meaning that when the simulation is running, it's almost impossible for us to know what event will occur at what time throughout the simulation run period. For example, we want to run the simulation for 1 day. We cannot know that how many events, how many arrive event will happen, how many load event, unload event, or start or end event will happen, and the time, the clock time for those events to happen. It's almost impossible, okay, for us to have a full picture of this. And only even if we have this a full picture of this, it's actually meaning that we don't need to run the simulation anymore because we know everything. The purpose of simulation is to see that we want to let the things going on, then to see that what will happen in the system, in the sense that the dynamic of this simulation model, the running of the model is actually depends on the triggering of the events or schedule of the events. Okay, so this is how the simulation run is driven by the events. Okay, so in that case, the next question, the third question we are going to ask is how those events will trigger each other. For example, when the arrive event happen, okay, when the arrive event happen, instead of just updating the state variable, like those number in the buffer, so how it will decide what to happen in the future, okay? When there is one load arrive in the system, so what are the other things that will trigger in the future?
I think the machine will take the load if it's variable.
Yes, correct. I think this is actually a very precise answer. Okay, when there's something arrive, it will trigger the starting of the service, but not only always trigger these things, it actually conditional. It's based on the condition that the machine is idle, then it will start, right? When there's arrive, then you will check the condition. If the condition satisfied, which actually the machine is idle, then you will start the service. Okay, you will trigger a start service event. This is correct. Okay, so any other things? Okay, so I think the next one, actually they will have another triggering relationship, but this triggering relationship is not the how to say a real like a logic, but rather it's actually the way we perceive it from the it's actually the way we digest. We're looking at the system. It's like one arrive event will trigger the next arrive event. Okay. So I mean, in reality, this might not be the same because you see that when there's actually when there's actually a production line, so every product when it comes actually is because of the last flow. And also in the reality, when in a service system, when a customer comes, okay, so actually each customer actually is making their independent decision. But here is only in the simulation world when we like generating those loads, the logic we are using is that we let one arrival loads to trigger the arrival of the next loads. Okay, so in that case, we can actually reduce the number of the events. Okay, we store in the future event list. Okay, so that's why here arrive events will trigger the next arrival. Okay, so this will be some things I think you need to know lah, but this is actually not from the common sense. And that's why here we have a very important concept called the inter-arrival time. Inter-arrival time actually meaning that how much time you want the next arrival to be apart from the current arrival. Okay, so this is actually a concept of the inter-arrival time, and also is a triggering relationship of the arrive event to itself. Okay, so this is about the arrive event. How about the load or start service? When the start service is happening, so what it will trigger? So which event the start service will trigger? Yeah, Hongdan, you want to answer?
Unload.
Unload. Actually, it's the
Yeah.
end service. Okay, unload or end service. Yes, correct. When something starts, okay, then if you know the processing time, then there will be one event which is triggered by the starting event is actually the ending event. Okay, so the end the service, which is here the unload event. Okay, so this will be the next event. The load will trigger by delay for how much time? The processing time, right? So the processing time will be the time delay between the load and the unload, actually the start and the finish event. Okay, so this is about the start service. How about the end service? When the end service is happening, when the unload is happening, so what we'll do? Okay, so I think in the common sense, you can see that when certain customer finish the service, we'll just leave the systems. Okay, but in the simulation world, so what we will do is that, okay, because when this a customer leave the system, so instead of just update the state of, I mean, according to itself, mean that, okay, so now the number of the loads in service is reduced by 1, okay, no problem. But also we need to realize that it actually create another opportunity for those potentially waiting in the queue. So that's why after at the time when this customer leave, so it also need to recall to see that whether there's any like a pending job need to be processed waiting in the queue. So that's why usually the finish event will call like a start event to happen. Of course, based on certain condition, it's only trigger when there is someone waiting there. Okay, if there's someone is waiting there, then the finish event will trigger another start event. Okay, so in this case, so actually you can see that this event diagram, okay, below, actually showing the relationship. Okay, about this load triggering relationship, and also how the event will update the state variables. And also you can observe that the state variable, the definition of the state variable is also implicitly like indicated here. So here we have this Q and M, etc. Okay, so this is another way to define the model compared to this one. So this we call the conceptual model, and this one we call is an event diagram representation. It's actually a formal way to define the simulation model in an event-based formalism. Okay, so yeah, I think this diagram will be very important for you to understand what does this mean, and also the important thing is after today's session, you are supposed to do a translations, okay, between this model, event diagram, and the simulation model written in the C#, the O2DES.NET. Okay, so with this, let's jump to the program to see that how can we modify from the previous model in order to achieve this. Okay, so if you still remember the last time, so what we are doing here is that here we are actually simulating the arrival of something, or maybe we can treat as a load, okay, to arrive into this system. So every time when it arrive, we just when this thing happen, when some event happens, okay, then we just do some state updates, okay, and also we schedule the next event. So this is some model we built last time. By now, with all the things we illustrated just now, so let's modify this model. Maybe we don't say modify, but actually we rebuild, we develop another model, but we still follow this structure. We need to have a static property, dynamic properties, and model, the initializer, and all the events. Okay, so let's first ask this a question. So just now, I think maybe maybe this is some things we know just now is what are those static properties we have in this system? So meaning that when the simulation is running, so what are the things which are not changing throughout the simulation run? Okay, maybe we can compare to what we have here last time, the inter events time. So if you use this concept, so what is not happening here? What is not changing here? Just now, who want to say something? Yeah, on that, yes. Yeah, Shinju, maybe you are next.
Sorry. I wanted to say the service capacity, but it's not related to the time interval.
Yeah, it's okay. It's okay. It's okay. No
Yeah.
problem. So the service capacity, the machine capacity will be 1. Okay.
Okay.
Then the next one, maybe Shinju want to say the next.
Yeah, like one machine and one buffer.
One machine
and one buffer, one queue. Yeah.
One machine and one queue.
Yeah.
Okay,
Static.
meaning kind of a structure lah.
Yeah.
Kind of structure. Okay. Yeah. Yes, correct. This is also something about. I think in this model, we rather than to say that we set this as static properties, we assume this is some things is not configurable lah. Okay, it's okay. So yes. But what do you say is right? What you say is right? Yes.
Maybe service time is also a constant.
Service time is also yes, correct. Service time, processing time. Yeah, and also other things. Monica, just now I see you are unmuted. Do you want to say something?
Sir, I don't think there will be any static property because if we can have for each customer, if one customer come for one, the service time, processing time will be either different. Yeah.
Okay, because it's randomized, right?
Yeah. So
Okay.
I'm not very sure.
Yeah. Okay. This is actually a very good point. And also, just now when we say a processing time or service time, it actually not very precise. Okay, in the sense that it should be the expected service time or expected interval time. Okay, so if we illustrate in this way, are you satisfied with the answer? So meaning that although that each customer may have a different interval time, may have a different processing time, but the expected
variable name will be same. Yeah.
Yeah, expected service time and expected interval time will be the same. Okay.
Yes, correct.
Unless in another case that we say, this is not a distribution, we just use a constant service time, constant interval time, then it's no problem. Okay. So yes, you are right. And also I think this is very precise in the sense, this is why we need to call this as a static property. So as long as it is changing, like what you said, we cannot call this as a static property, but rather we need to identify what are the static portion behind it. So for example, processing time, if it's a random, so it's a dynamic, so we cannot call this as a static properties, but actually it got some static portion behind, which is actually the expected service time. Okay?
Okay, sir.
Yeah. Okay, I think you raised a very good points. Okay, so in that case, yeah, let's come back to this model. Okay, to define all the static properties we just mentioned. Okay, so the first one, sorry, English. Okay, so the time span, let's first have a expected expected service time. Okay, then similarly we also have a expected inter-arrival time. Okay, and just now we also mentioned about the server capacity, right? Server capacity. Okay, so this will be another one. Okay. One more thing is just now Xinju mentioned about the number of servers, number of queues, right? Yeah, so I think probably in a later, more advanced case, okay, we can also set this one as a static properties. Okay, we can like put another thing, that number of servers here, number of queues here. But the thing is, when the number of server or number of queues increases, okay, then we can see that the model structure will change in the way that we need to see that how multiple queues were connected to the multiple servers, okay? And also when there's a multiple server, whether they will have a different processing time. So in that case, I mean, a lot of other issues we need to be clear, okay? So here is actually assumption of the model we have here is that we consider only a single queue, a single server, but the server might have a multiple capacity, but the processing time, the distribution of the processing time are the same. Okay, it's only one identical processing time. Shinju, I think this is clear for you, eh?
Okay.
Yeah. So what you said is right, but this one we can consider in the later phase. But now let's assume it's just a single queue and single server. Okay, so now is that I want to show to you that the way we come up with these static properties. So now is you can see that every time is that we are doing the static properties in this way. So in the case that later in the constructors, instead of one parameter, we have a multiple. We need to have a multiple parameter, which a little bit complicated. Okay, which a little bit complicated, meaning that if we want to add another static property here, then we also need to do this configuration one by one. So it's a little bit troublesome. So what we can do is we can actually leverage on the encapsulation, okay, of this object-oriented programming to make this a little bit simpler. Okay, so how can we make it simpler? Is we create another class. So we see that this class is actually for the model statics. Okay, so instead of putting these three attributes properties here, we put it here. Okay, we put it as a number as a part of this model, the static components. Okay, and instead of to call this as a private set, we just make it a public. Okay. So the good thing is when we specify, we can anyhow like freely define any like model statics. Okay, static meaning this is a set of the static properties. We can freely set up, I mean, read and set any property of this. So this is basically just a data structure for us to encapsulate all the static properties here. But rather here, instead of these three properties, we just have the model statics. Okay, and this one we call the config, which actually is the short for the configuration. And for this one, we set a private setter. Okay, so here you see what is the difference. We actually encapsulate these three properties into one object. Then in that case, it will be simpler when we do this. Is we simply say this will be the model statics, then config. So what we simply do is we do not need to do this. I mean, set all of the properties to them to each of the means according to a different parameter, but rather we can simply do this one. We let config equals to the config which are passed in. Okay. So we are handling them as a whole. So this part, are you able to understand? Okay. So if you're okay, so
Yes.
so if you're okay, we continue from here. It's basically encapsulation. Okay, so this is how we do the static properties. Then let's look into the dynamic part. Just now we see that how many dynamic property we have? 2, right? One is the number in the queue. The other one is a number in the server, right? So here we need to change this dynamics to be the number in the queue. The other one will be the number in server. Okay, is this clear? Okay, so just now we only
Yes, sir.
identified 2 state properties. So here we do these things. Then remember, every time you define the dynamic properties, remember to set the initial value to it. Okay, so either you can do in this way, 0, 0, or you do here, number in queues. Okay, number in queue equals to 0. You can choose either way, but I think now in this case, make it simpler. We just do in this way. So meaning that at the starting of the simulation, it's a start with empty, but it's not necessary every time it's 0. I mean, for your study, so if you want this one to be like static hot, okay, in a way that it's not cold static, I mean that you want the simulation to start with some things already inside. Okay, so in that case, you can set this value as positive. Okay, but now let's make it simple. Okay, we let it start from 0. You can also remove this thing in C# because the initial value of the integer will always be 0. But I think it's better to explicitly tell what is the initial value. Okay, so by this, we actually finished handling of the defining of the dynamic property, the state variables. Okay, so now let's move to the events. So just now, how many events we have defined, identified? 3, right? If you look into this image, this event diagram. So basically this arrive, load, let's change the name to start and finish. We have a arrive, start, and a finish. We have this 3 different events. So that's why without any other things inside, let's just make the structure, define the structure of the events. We have this 3. So we have this arrive event. We have the start event. Okay, we also have the end events. Okay, so we define this a 3 event at the beginning. So this is a simply corresponding to, okay, just drawing this 3 circle. Okay, so now we want to go through events each one by one. So according to what we just discussed, when a right event happens, so what we do is we actually let the queue length to increase by 1, right? You can see the state variables here. We simply increase the queue length by 1. Then the second thing we're going to do is to see whether the server is idle. So if it's idle, meaning that whether its full capacity is met. If it's still less than the number in server is less than the capacity, then we'll trigger a load event, the start event. Okay, and in any case, okay, we will trigger the next arrival based on the inter-arrival time. Okay, so let's do this 1, 2, 3. Let's do these 3 things in our model. And also, before that, I just want to highlight this part. This rectangle, okay, this box, actually meaning the initial status, meaning that the queue initial value is 0, the m equals to idle, meaning that the number in server is 0. Okay, so this actually corresponding to what we have here. Okay, so this is actually the box. And also now we define this arrival, this circle. So now we are going to this 1, 2, and 3. You should do this 2, 3, 3 things for this arrive. Okay, so for arrive event, the first thing is we let a queue number to increase by 1. So basically a number in queue plus plus. Okay, so the first thing is done. The first thing is done. So now let's go to the second one, which we need to check whether the machine is idle. So if it's idle, we schedule the load event at a time now, okay, at a current time. So I will show you what does this mean. Okay, so we need to add a condition to check if the server is idle, in the sense that we need to check the number in server, whether this one is small than the server capacity. Where is the server capacity? Where the server capacity is defined? It's actually a static component, right? So if it's a static component, it should be under this config. Then under this config, it should be this one. Okay, so what we do is we check whether this is smaller than config.server capacity. Okay, so yeah, this is doable is because of the encapsulation. Now we can encapsulate these static components properties under the config object. So that's why we can do this in this way. Okay, so when this condition is satisfied, so what we do is we will trigger a start event. Okay, you can see that the triggering of the start event actually have a two-way. The one way is doing this. Okay, so if this condition is satisfied, then we'll let this to happen, let this happen. And also we can do another way is actually we can schedule these events. Okay, if following this, we do not specify any time span or etc. Okay, for example, like the last time we actually have some time span after this. So if we remove this part, so what does this mean? It's meaning that it actually schedule this event at the current clock time, So I mean, in this case, it will be, the effect will be same as you just have these things to call this a method to execute it. Okay, so these two will be equivalent in the effect of running the simulation model. I mean, for the current case. So later I will show you what is the difference. What is the difference between these two approach? So now let's, I think now let's do this one first. Okay, and I think in most of the case, try to use this one by default setting. Okay, so this is schedule a start. Actually, schedule meaning this arrow, meaning this arrow. You can read this as a schedule in O2DES.net. Okay, so this like this a small curve here. You can treat this as an if condition. So if this thing is true, then you will schedule this one. If there's a no t, no time delay, like this one and this one specified there, then it's meaning that when you schedule, you don't follow a time span. Just a schedule at the current time clock. Okay. So after this one, what is the third thing? It will schedule the next arrive, right? But this one is with a time delay of inter-arrival time. Okay, and this inter-arrival time is randomly generated from the distribution of the inter-arrival time. So now we have the mean of the inter-arrival time. So now let's just assume it's exponential distribution. So I'll show you how we can generate this number. I think we also talked about this last time. So the third thing will schedule the next arrive events, okay, after some time. Okay, so let's say in the configuration, we actually have this expected interval time. So if you do this one, it will be a fixed interval time every time. But if you want to make this as a random, so what we can do is we call exponential dot sample. Okay, you need to give a random stream as we illustrated last time. So we have this sample default. We have this default random stream. Then we give the mean, which actually the expected interval time. let's see whether this is the mean or the rate. It should be the mean. Okay. Yeah. So that's all. Okay. So you see that this is actually the TA. This is actually the TA. Then this schedule is an arrow. This is a point to the arrive event. So exactly is what this arrow is trying to say. Okay. So now you can see that in this circle, actually, we finished the statement for this bracket, this part, and this part. Exactly the 3 statements. Okay, here. Okay, this is actually for the arrive event. So let me just say clear about is what the difference between the schedule start and the start bracket. Okay, so if we do the schedule start, meaning that all the things in this start event will be scheduled or put into the future event list. But whether those things here, for example, dot, 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 okay? So whether those are dot, dot, dot here, okay? Whether this part of the statement will be executed here, if we do a schedule, someone can just give a guess. Monica, you want to give a guess?
Sir, it will start, sir. It will print.
Okay, the thing is it won't. Okay, so when you schedule,
Okay.
meaning that it won't execute it now. Okay, if we do this one. So whatever written here will not be executed here.
Yeah, because 0, it is 0.
It's
It
no,
is not less.
because it's a schedule. So when the schedule, meaning that it will not execute it now. It will not execute it here, but rather it will finish the third statement at the 35. Okay, if you finish one statement, second statement, third statement, okay, so only after all the 3 statements is finished, then it will look into what are the things have been scheduled. So if you look in the there's something scheduled in the future event list, then you will follow by this. So okay, let's make it simple for illustration to say that if we do in this way, then the 33 will be executed first, followed by 34, followed by line 35, followed by line 40. Okay, so if we do a schedule, this is what it will do. Okay, so this will be the sequence. But rather, if we do in this way, so what will happen is when they execute this part, we'll jump to 40, finish 40 before they come back to execute the 35. So in that case, if you do in this way, so the sequence will be 33, 34, 40, and 35. So can you see the difference?
Yes, sir.
Okay, so this actually make a difference at a sequence of the executing the code. But I should say that for this model we are constructing now, does not make any difference. Okay, yeah, but I think that by default, let's use this way lah. Let's use this way. Only when you make sure that there's a necessary to like or maybe have a special benefit of executed directly, then you use the start bracket. Otherwise, always a schedule, even it's at the current time clock time. Okay, so let's make this as a convention now. Okay, by default, let's do the scheduling. Okay, so this is about the arrive. This is about arrive. So now we move to the next circle, which is actually the load. So what the load will do is the load will do the update. Okay.
Sir, sorry to interrupt, sir.
Yes.
Can you come back to that code, sir?
Yes.
So, sir, if we have the print statement in arrive and we
Yes.
have the print statement in console.writeLine, then we will come to arrive first. So it will print arrive. Okay.
Yes. Yes.
One
yes.
time.
Yes. Yes.
Then,
yes. Yes.
Then
So yes. So here, if you see here we got a console write line. Arrive. Okay, so if you print arrive first before start, for example, here we got a start. Okay, so in this way, it will print arrive first, followed by start. So if you do this one, if you do the start bracket, then it will be the start first, followed by arrive. So in that case, in some of the cases, it's not right, okay? Because I mean, common sense, you arrive first. If you finish all the things that need to do at arrive before they do the next thing, okay? So I think this is actually a common, intuitive way to understand why do we need to do a scheduling.
Yeah, okay, sir. First arrive, then
Yes.
it will go to start,
Yes,
Then
yes.
again there is
Then
a
it will
schedule
arrive.
arrive.
Yes,
Then
yes.
again it will arrive.
Yes, yes. So
Okay.
here, if you have the, for example, and later we will show you when this is parameterized, okay, then you will see arrive the first load, start the first load, followed by arrive the second load, start the second load. Okay, it will follow this sequence. Otherwise, if you do this a bracket, I mean directly a bracket, then it will be a
Then it
little
will
bit
jump.
different. It will be the start of the first load, arrive the first load. It's a
Okay.
little bit strange when we see the outputs. Okay.
Yes.
Yeah.
Sir, one more question. Sir,
Yes.
like you have config dot expected inter arrival time.
Yes.
So many times we are given the time. So that time we will hard code it the number. If we
This
have
one
the
it doesn't matter because this
doesn't
one
matter.
is to say there's a parameter. We leave those things outside of the model to decide. So whether outside is high coded
Yeah.
or outside is coming from a GUI, this is another story. We don't care because now we
Okay.
only focus on the model. Okay.
Okay, sir. Okay.
Yes.
Okay.
Okay. So now let's just finish. I think today we another 15 minutes. I try to finish all the event and let it run. Then yeah, maybe later we can go through all the other question. Okay. So let's look into the start. So what the start will do is we do the state update first. So basically we'll set M to busy. So I think in more general case, we just increase the number in server to be increased by 1. Then the queue number need to be reduced by 1. Okay, so this is the update of the state variable, followed by triggering the unload. Okay, so you can see that this is 1, 2, 3. These are the 3 things the start event is doing. Okay, so we do the first thing, which is actually the update. So we let a number in server to increase by 1. Then we let a number in queue to be reduced by 1. And also we want to schedule any event, okay, after the service time. Okay, the same thing is if you do in this way, it will be a fixed time, but now we want it to be random. So that's why we'll do exponential dot sample. Okay, random default random stream followed by this one. Okay, so in this case, we'll use service time to generate exponential distributed random variable and schedule them. So this is 1, 2, 3. These 3 lines will corresponding to this 1, 2, and 3. Okay, these are 3 actions, 3 things. Okay, this start event will do. Okay, so this is about the start event. Then, okay, any questions now for this one? For start event?
No.
Okay,
No.
so if not, we move to the last one, the last event about the finish event. So finish event, how many things we need to do? 1 and 2. Okay, based on this thing. The first one, we need to set this one to be idle. So I think in more general case is that we reduce the number of servers to be number in server to reduce it by 1. Then we check condition whether anything's in the queue. If there's anything in the queue, then we trigger the start event again. So let's do these 2 things here. So the first one is we'll reduce the number in server to be by 1. Then we will check, okay, because it's a condition to see that whether the number in queue is larger than 0. If it is, then you will start again. Okay, as I mentioned, is that now we better use the schedule. So we do in this way. Then similarly, we just print out the message to see that this one is end. Okay. Then I think let's try to put into the clock time here. So let's do in this way. I print a clock time, arrive. Okay, let's copy these things. Okay, we have this arrive, start, and end event implemented. Okay, so now is that basically you can see that this set of the code corresponding to what is written in this graph. Or in the sense that later, so our team can actually do these things. We can come up with this tool. So people, whenever they draw this event diagram in this way, then automatically will convert or translate it into a C# code. I think this is some things our team can do in the future. I think this tool will be very useful. But you can see that if you compare the code with the drawing, actually there will be one thing that's still missing, which means it's actually appear here in the diagram, but it's not in the code, which is actually this arrow, okay? This arrow. Meaning that when this is initial condition, then which event is triggered at the beginning of the simulation? Because you see that all the event is actually triggered by other events, but at least there will be someone will be triggered at the beginning. Okay, so yeah, so then all the other things can follow. So this arrow will be important. So where to write this arrow? Okay, so now we see that this actually array event is pointed by this arrow. So what we are going to do here is to put it here. We need to schedule the array events at the beginning when the model is constructed. So in this constructor, okay, so after we set all the static properties, this will be the first thing we're going to do. Okay, so now we finish building the model, okay, in this way. So now we go to the program. Let's do in this way. Now the toy, the sandbox is ready. The toy is ready. Now we are going to play with it. So when we play with this, always do the first thing is we set up a configuration object. Okay. So this will be new model statics. Okay. We'll set up a new configuration object. So this object you are going to give all the static properties of this one. So for example, the server capacity we set it to 1. Then the expected interval time we set to maybe 4 minutes, 4 minutes. Okay, let's just do 4 minutes, for example. Then expected service time, we let it to be slightly longer than this 4 minutes. Sorry, slightly shorter than this 4 minutes. Okay, so in that case, there won't be an expansion of the whole system. Able to reach a certain like a stationary status. Okay, so yes, okay, so this is actually the static part of the model. So now we need to create a dynamic part of the model. So instead of define each parameters here, we can simply give this passing this config object. Okay, then the seed we let it to be 0. Then we let the simulation run. Okay, but if we do in this way, then it will just run infinitely. Okay, because it will always be a new arrival, new arrival to come. So I suggest we change this one to some finite time frame. For example, we run this for 1 hour. Okay, then we see that. Sorry, we don't use a while loop. Okay, so just do this, run the model for 1 hour. Then we can see what is going on. Okay, so we'll play. Okay, so we can see the different time. First start, arrive, start, end, arrive, start. We can see there's a sequence. Then sometimes we can see that it's not necessarily always arrive, start, end, but sometimes the 2 arrival at the same time, then we end, then start again at the same time because there's someone in the queue. So actually it's very interesting to observe this sequence. Okay, but in order for us to understand more of what is happening, I suggest that here in the output, we also putting like some more information like what is the number in the queue, and also is what are the number in the server. Okay, so here we put a number in queue, and here we put a number in server. So let's bring up this information, and so that we can have a better understanding of what is happening inside the system. Okay, So here you see that at the time 0, there's a 1 arrive. So when arrive happens, actually the queue increased by 1, server is idle. Then after that, okay, then we, at the same time, because it's idle, then subsequently we have a start event from 0. Then it's actually this one immediately go to a server to process. Then after some time, 36 seconds, it's end, then it become idle again. Then another one comes, join the queue. Then before it's end, and another one arrive. But in this case, it have to wait in the queue. So when it's end, this one become empty. Then immediately will call another start, etc. So if you follow this one, you can actually manually check all the dynamics of these systems. Okay. So what is important, okay, about this model is that it can actually tell us some information. Okay, for example, if we want to have a curious of what is the utilization of this machine and what is average queue length for this queue. So in that case, we need to make sure there's sufficient space. We'll have some question about that. But if you want to have such kind of questions, what we are going to do is we will draw some things on this right. Okay, so here you can see that we have a different time point. Then we can see that this value actually changed from a 1 to 0, 0 to 1, sometimes 1 to 2, etc. So if you want to draw this, and sometimes the queue can even be 4, 3, or sometimes can be larger. So in such kind of the case, so what we can draw is using this kind of graph. We have a number in, for example, we have a number in the queue, number in the server. Then we have this time horizon. Okay, this is a time horizon to indicate a different when the event happening at a different time point. Then we can see that this value of each variable that changed. Okay, at the discrete time points. Okay, so in that case, if you want to ask a question, for example, about what is the average queue length, so we just look at the statistics of the queue to just see how many number in the queue change dynamically according the time, along the time. Then we can look at average area under the curve, meaning all the gray area. We can see how large is this area divided by the total length of the time. Okay, so in that case, we'll see that, okay, this is average number of the queue. Similarly, when I look at average number in a machine, we can actually calculate this area. Then we can see that this area, this maximum height will never exceed the maximum capacity of the machine. Okay, so in that case, if we use this area divided by the total length and divided by the maximum height, okay, of this curve, which is actually the capacity, we can actually go the utilization. Okay, so this will be something that maybe I will tell you how to do this in the next session. So we don't need to do this manually, but rather we can use a tool, very powerful tools in our O2DES framework called the hour counter. Okay, for us to do such kind of statistics. Okay, so by now I think for this session, you just need to understand the important thing is this is a conceptual model. How to come up with this is an event diagram model comparing to this one, and how to translate this event diagram model into the C# code of this O2DES.NET model. Okay, and each component of it, how does it corresponding to the graphics? Okay, and understand the running results. Okay, which we are showing here. I think that's all you need to understand from this session. So any questions from you?
No, sir. Actually, as in your slide, there is atomic queue. So I think that is similar to this, right?
Sorry, MM's.
Q atomic.
Yes, correct. Actually, it's the same.
Same.
MMCQ. Yeah, actually, it's the same.
So,
Okay.
yeah, there are few things like hourly arrival rate. So you have given it as a static property. So maybe the model, maybe the event graph is different. That is why you have given them as static.
Yeah. So in that one, we actually have the hourly arrival rate, but here is that we
don't
just
have
look into the. I mean, this is the same. is for this one, you take it as an hour. Okay, you look at the time span, you convert it into the total hours, then you take the inverse, then it become the hourly rate. Okay, so actually the same information, the same thing.
Okay, same
This
info.
will be corresponding to hourly will same corresponding to the hourly service rate. Okay, just the other way of representing the information. Yes.
Okay, and then there is HC in queue dot average count. So you are returning that. I think that is from
Which part? Which part? Are you talking about this part of code?
no, sir. In dynamic properties, you have written get return HC underscore in queue dot average count. So
I think we don't need to
yeah.
refer to that one. We don't need to
Okay.
refer to the old
Okay.
material. Yeah, we just look
Okay.
into this one.
Okay.
As long as you are able to understand these things.
Yeah.
Yeah, but I think you can find a synergy between these two. Yeah, for example, maybe I'm previously written in a different way. So I think after this session, if you have still have any questions, you can
Okay.
actually just highlight those part and paste in the group. Then we can discuss offline.
Okay,
Yeah.
sir.
Okay, Ken.
Yes,
Yeah.
yes.
So
Thank
any
you.
other questions? I think if not, now it's
I
already
have
1 hour.
another
Yeah,
question.
yes, please.
Yeah. Just now, as for the start, you have checked if the if the number in the queue is less than the queue capacity, then schedule the next event. But what if the number of load in the queue is equal to the queue capacity?
Queue capacity, right?
Yes.
Okay, you see is in this model, in this problem. So just now, when we discuss about the static properties, we do not really mention the queue capacity, because in this MMCQ, actually the queue capacity is not tracked. Okay, meaning that we assume the queue actually have infinite capacity. So this is actually assumption of this model. Why this is assumption is otherwise, I mean, some of the properties will be violated, okay, to derive the queuing theorem, okay, to derive the queuing theorem. Why is in that case we may have certain how to say missing rejected arrival, okay, because you see that for this buffer, if the buffer have a capacity, then it may happen that when someone arrive, then the capacity is full, right? So in that case, what should we do? What should we do? So in some of the case is that people assume when the capacity is full, then this arrive will just be disappear, will disappear. Okay, so this is called rejected arrival. Okay, when arrive appear, capacity is full, the first process capacity is full, then we can see that is actually rejected, okay? Rejected arrival. So when the first queue or the first server, or anyway, the first process of the whole system has a finite capacity, then there will be a problem for the rejected arrival. So in that case, what will be the problem caused is that the arrival rate will be different from the processing, the input rate will become the different between the output rates. So when you look at the right-hand side, if you take a look of what are the flow of the rate, okay, to the outside. So actually it's a different, it's smaller than the left, than the incoming rate, right? Joyce?
Yes.
Yeah. So in that case, you can see that these two sides, okay, the rate is different. The incoming rate is larger than the outgoing rate if the first process has a finite capacity. Can you understand this part?
Yes. Then
Okay.
I have another question is
Okay, maybe let me finish. So
okay.
another way to handle this is to say that, okay, so if the first queue is full capacity, then you just reserve this arrival, this load somewhere else. Okay, maybe just outside the boundary. Whenever this is got a capacity, then you put this in. Okay, so in that case, it's indifferent from adding another queue in. It will be like a two queue. One queue is infinite capacity, then another queue with a finite capacity, followed by a server with a finite capacity. So in that case, it's the same as to say that you have infinite queue at the beginning. Okay, so this is actually the second way of handling that.
Okay, thank you.
Yeah, yeah.
Then I have another question. Got confused about the triggering of the start. So need to check the capacity of the machine, right?
Yes.
Yeah. What if the machine is fully occupied?
Mm-hmm.
What will happen?
Okay. Yeah, it's actually a very interesting problem to see that when the arrive is happening, then you need to check the capacity, right? So here we see that if it's a smaller, meaning the capacity still got remaining vacancy, then you will start. But it doesn't really say that if the capacity is full, so what we're going next, right?
Yes,
so
yes,
I think this
yes,
is your question now. We
yes,
have
yes.
if, but there's a no else. Okay, so actually this is actually very tricky part, and also the part I like the discrete event simulation the most is that this situation actually called an called indefinite delay. Okay, so definite delay. Okay, definite, what does this mean? Meaning that the delay is actually, for example, here, you want to delay the next arrival, but how much time you want to delay is known, although it's like a random distribution, but as long as you generate this random number, you know how much you will delay. But here, when there's a no start, what will be the next start? It's unknown, okay, to this process. So this one, the start will call the indefinite delay, meaning that you don't know how much time will delay the start when the capacity is full. Okay, so I mean this is a direct answer, but you will see that what is the time it will start is actually from here. It's actually what time it will start will depends on the other load. I mean the previous load currently being processing in the server. So indefinite delay doesn't mean infinite delay. Okay, this is different. Okay, indefinite delay meaning that the delay time is not known, but doesn't mean it's a infinite delay. If infinite delay, that means that it's a deadlock. Okay, it's a deadlock of the system. So it will not be the things we're going to simulate here. Okay, it's just that the delay time is not depending on the load who currently arrive at this event. Okay, but rather how much time your delay will depends on other loads in the system, which are doing process at other places. Okay, so in that case, which one will be depends on? It will depends on those loads currently being processed in the server. So when this end happen, okay, then it will pull, then you will see that if the number of queues is larger than 1, why is it larger than 1? Because just now you added this by 1. Okay, sometimes it's added by 1. Okay, so if this is larger than 1, you will start a schedule a start. Okay, then this start event will be triggered. You see that either the start event will be triggered by arrive event or this event. So if it's a triggered by this event, it happens when it's a capacity is available. If not, it will trigger indefinite delay, then it will trigger later by the end event. Okay, and this one you can also see from this event diagram. So this one, when this condition is satisfied, it will trigger this one. Okay, otherwise it won't do anything which cause indefinite delay. Then this event will instead be triggered by other part of the system. Okay, so to him, the delaying of this start events which are triggered by this one is called indefinite delay for him. Okay. Yeah, so I hope this explained the concept to you.
Yeah, it explains clearly already. Yeah,
Yes,
thank you.
Yeah, okay. So any other questions? Okay, so if not, okay, let's call it a day. And yeah, so again, so Monica and Joyce, I may need your help to summarize what have been taught today. Okay, then tomorrow, the same time, let's continue. I think tomorrow I will try to talk about the attribute of the load, the simple function of the hour counter. Then probably after that we'll go back to some of the previous questions to go through some of them. Okay?
Okay, sir.
Yeah. Okay. Thank you.